This video is for Lab 2, Motion of a Falling Object. In this lab, we were set out to produce and analyze an example of the motion of a falling object using both a real-world example and a computer model. Both the weight force and a drag force acted upon the dropped object. These could be modeled fairly well, but not perfectly. The motion of a falling object is dependent on Newton's second law, which, in its final form, is final velocity equals initial velocity plus the net force over the mass of the object times the change in time. In order to calculate the net force for this instance, we find first the weight force, which is the mass of the object times the force of gravity times a direction vector, j hat, plus the drag force, which is negative b, a proportionality constant based on the surface area of the object, times the absolute value of the velocity squared times the same directional vector j hat. We end up with F net equals the weight force plus the drag force. The first task was to film the motion of a falling object and analyze it using Tracker. Here you can see a cup being dropped open side down in order to ensure a drag force, and the positions tracked by these red diamonds. You can see that there's a slight arc downward followed by a nearly straight line, and further down the time and position data accordingly. The data from Tracker was then entered into Python in order to create a model. First, we see that we have the cup's mass, followed by the initial position, which is the zero vector, and the initial velocity, which is also the zero vector, because the cup starts at rest. We set delta t equal to a fairly small time interval to create the best curve, gravity equal to 9.8 meters per second squared, the standard value, and the j hat vector to be a unit vector of 1 in the y direction. Then we have b, which is the proportionality constant mentioned earlier. This was derived from an attempt to match the model to the graphed data that will be seen shortly. For the calculation loop of the position of the cup in Python, we set the time equal to the total time interval that the action happened, and then we model drag through the ball's velocity squared times the proportionality constant b times j hat. Then, in order to get F net, we add the weight force, which is negative mass of the cup times gravity times j hat. This is followed by Newton's second law, which we saw earlier, which is the ball's initial velocity plus the net force plus the mass of the ball times delta t, and a new equation to update the ball's position, which is the initial position plus the ball's velocity times the change in time. Here we see the Python model run first drag, the yellow arrow representing the weight force, and then with the yellow arrow still representing the weight force and the blue arrow representing the drag force. Here we see the experimental data in blue mapped with the model position in red, as well as the model position including the drag force in green. We see that both models overpredict the position of the cup. However, the drag model comes closer to the experimental data in the beginning and the end. This overprediction could be due to the fact that the cup wobbles slightly in the air, leading to an imperfect drag force. Neither of my models predict a terminal velocity. However, we know that the slope of a velocity versus time graph would transition from a curve to a constant velocity as an object reaches terminal velocity. This is the point where the drag force and the gravitational force are equal, resulting in F net equals 0 and a constant maximum velocity. Neither of my models show this. However, the one with drag comes close, as can be seen when the model is run in Python and the drag force arrow and the weight force arrow are nearly identical in magnitude. the terminal velocity for an object is always the same, independent of initial velocity, because terminal velocity depends on surface area, drag, and weight, gravity, not on the speed that the object starts at. If given enough time, an object will always fall and reach a terminal velocity, and that terminal velocity will be the same as long as the object's weight and surface area do not change.